Good morning, friends. I learned from many of you that you had a wonderful day yesterday with the morning visit to the Chandrayaan facility and then in the afternoon to HAL. So thanks to Mr. Nayak for arranging that visit in that short notice. This morning, the whole day actually is quite an exciting day, a combination of subjects to listen to. But before I go into that, let me tell you some of the changes. Mr. Abhinav Bindra's lecture will be at 2 o'clock in the place of 11:30. And we are trying to see if we can get him to join you for lunch. So that's still something which we are trying. And another program which is scheduled at 11:30 is the presentation by Brigadier Devendra Kapoor on the challenges of leadership in intense counter-terrorist operations. And Mr. N.D. Sharma will be chairing that session. And in the evening, 5 o'clock, again with enthusiastic feedback that I have got from all of you, there will be a session of sharing experiences which Dr. Sai Baba will be coordinating. Dr. Sai Baba and Mr. Govardhan will be coordinating. So kindly get in touch with Mr. Govardhan or Dr. Sai Baba to coordinate that session at 5 o'clock of sharing experiences, but which will particularly focus on leadership issues. This morning, to begin with, we have something quite interesting and a bit different from perhaps the last 2 days. Professor B.V. Sreekantan, and a very senior scientist of this country, to speak to you on science at the edge and on the edge. And to chair his session, we have an equally famous and with significant contributions, Dr. K.B. Sainis, the outstanding scientist and director, Biomedical Group, Baba Atomic Research Center, to chair that session. So now let me request Dr. Sainis to start this morning and chair the session. Thank you.
Thank you very much, Professor Sangeeta Menon. Respected Professor Sreekantan, Professor Sangeeta Menon, ladies and gentlemen. A very good morning to you all. And I feel both proud and privileged to be chairing a session where a person who had an iconic status during my formative years as a researcher, Professor B.V. Sreekantan, former director of TI for Mumbai, will be speaking to us on science on the edge and science at the edge. Science today drives everything around us. But if we go back, then we find that it has been a long process of acquisition of knowledge. When I had not learned much about science, almost 50 years ago as a school kid, one of my teachers, who was not a science teacher incidentally, very simply paraphrased a shloka from Bhagavad Gita. And it read, Mukam karoti vachalam, pangum langhayate girim, yatkrupat tamaham vande, vijnanam yuganayakam. Vijnan, the science, as some say, is a systematized knowledge, a knowledge about our universe, both animate and inanimate objects. A quest for searching its structure, searching its function, the laws that govern that function. Over the years, we have continuously acquired this knowledge. And in the acquisition of this knowledge, we have refined our methods of acquiring this knowledge. As a consequence, today we can see what now I could normally not see. We can imagine much beyond what a poet could have imagined. And with that knowledge then, we have been able to improve the quality of human life. Today we have astounding developments in the fields of electronics, computer science, biology, and all other fields, astronomy, physics, and so on. Entire human genome has been sequenced. Genomes of more than 250 different organisms have been sequenced, whether they are plants or bacteria or small organisms. And with all this knowledge, we are even able to trace back history, go back to find out who the first mother was, What is the history of all these objects in our planetary system? So with these kind of questions coming up, science has really amazed us. It has astounded us. It has perplexed us, and it has inspired awe. Therefore, today we are at the edge of a technological revolution brought about by science. But then, friends, science has a Jekyll and Hyde personality. Inasmuch as it has improved our lives, it has also brought in its wake technologies that are meant for mass destruction. Technologies that are meant for destruction of our environment, the very basis or very nurturing place where we sustain our lives. In the process, we started wondering, are the foundations of civilization intact? Or are our concepts of morality, ethics not being shaken? Where will this science take us? So therefore, today we are on the edge. Science and society, both are on an edge of a precipice of destruction unless we correct our methods. So we have to go back and ask those philosophical questions as to what is the purpose and meaning of the existence of the objects in our universe. That, ladies and gentlemen, is philosophy of science. To talk to us about it then, we have none other than respected Professor Sreekantan. He is a visiting honorary professor at NIAS for a very long time now. He is chairman of the Gandhi Center for Science and Human Values at the Bhavan in Bangalore. He is the editorial fellow of the Project on History of Indian Science, Philosophy and Culture. For 45 years, he has carried out fundamental research in the field of cosmic rays, in the field of high energy physics and astronomics. He was director of TIFR from 1975 to 87, and then Sir Srinivasa Ramanujam, professor of the Indian National Science Academy there from 1987 to 92. His outstanding research work has been documented through more than 200 publications. He was the fellow, he had the distinction of being the fellow of 3 of the most important scientific academies in the country, the Indian National Science Academy, the Indian Academy of Sciences, Bangalore, and National Academy of Sciences, India, Allahabad. He has been honored with R.D. Birla Award of Indian Physics Association and has held visiting positions in various universities in the United States and Japan. More recognition came by way of Sir M. Vishweshwaraya Senior Scientist Award of the Government of Karnataka, and last but not the least, the great civilian honor of being called Padma Bhushan. On your behalf and on my own, ladies and gentlemen, I now request respected Professor Sreekantan to give his discourse on science on age and at age. Professor Sreekantan, please.
Dr. Sainis, ladies and gentlemen, I'm indeed very happy to give this lecture and this 44th course of the National Institute of Advanced. I'm sorry, not 44th, it is 23rd course. 44th comes because of day before yesterday's event. 23rd course of the National Institute of Advanced Studies. I happen to have spent about 20-30 years in the company of J.R.D. Tata as a member of the Tata Institute of Fundamental Research, and he was the governing council's chairman. So I knew his mind quite well, and when this institution was being formulated, he used to discuss with us the purpose and objectives of such institutions. And one of the important things he emphasized was that people in the various administrative services and people who are scientists but who are in various administrative positions, they should know what is happening in the frontier areas of science, technology, social sciences, economics, philosophy, every branch of science. They should really know what is really happening, because what happens to these gentlemen, people like you, is that because of your preoccupation with the present work, you try to know something about what is happening around in the world, but not in great depth. and much of it will be through newspapers or some magazine articles, etc. So Mr. Tata's idea was that you should really get exposed to what is happening by experts in the field. In fact, the whole idea of these courses, etc., was essentially from that point of view. So today I'm going to tell you something about what is happening in the frontiers of science. And I'll try to be not so very technical at all as far as possible, but a certain amount of technical discussion will be necessary to present what is happening right in the forefront. Now, the general outline of my talk will be as follows. I will tell you why I have called my talk the Science at the Edge and on the Edge. When I say something is on the edge, as you all know, it means there are unpredictable consequences. It may be for the good, it may be for the bad. And this has happened several times in the history of science. You know, when the atom bomb was developed in the Manhattan Project, just a few days before the first trial at Bikini Atoll, some of the scientists got very shaky. They started wondering that if we explode such a bomb, they had to test it out in an island called Bikini Atoll. And the worry that they had was that what if the hydrogen in the atmosphere catches fire and the entire Earth is caught in fire? That means the fire spreads and all the hydrogen and oxygen in the Earth's atmosphere becomes combustible, and then the whole Earth catches fire. This was a very genuine worry which hesitated many of the scientists to go ahead with the testing of the bomb. Then two of the scientists who were very much involved in the project, they went to Chicago and then to bring Professor Fermi, who was really an expert in this whole area, and to consult him whether they should go ahead with the test. Then Fermi came with them by a night train. This is beautifully described in several books, this particular incident. And the whole night in the train, he was making all kinds of calculations, whether it is possible that with this explosion, the entire atmosphere will burn of the Earth. Then by morning, he was convinced no such thing is going to happen. And he went and gave green signal for the test to be done. And the rest is history. You all know now. Several bombs have been tested, and two of them have been exploded to the serious consequence of the Japanese. Now, we have come to a similar situation by an experiment that is going to be tested at an accelerator called the sun. Some of you might have read in the newspaper whether there is going to be, as a result of the experiment that is going to be tested at CERN, what is called a mini black hole is going to be created, which will start gobbling up all the material around the laboratory, then will become bigger and bigger and bigger, and then ultimately whether it will swallow the entire Earth. This kind of fear was expressed. Some scientists again had serious hesitation in starting the work. I mean, the collider was completely ready for testing, but there was a lot of opposition by some scientists. But again, some experts felt no such thing is going to happen. But there was another reason why one need not have feared, but at the same time, many were not prepared to believe that. You know, we are continuously being bombarded by very high energy particles called cosmic rays. In fact, that's one of the areas in which I worked. And in that, when it comes, the cosmic ray comes and collides with the air nucleus, a similar situation arises. You can create many types of particles. So the argument was that if any such thing had happened, then if mini black holes were created, long ago the Earth would have been destroyed. So there were people who were not afraid of this experiment being tested. But what did happen was, about on September 26th or so, they started the accelerator, but unfortunately the accelerator developed some other problem, and there was a serious helium leak, and the entire tunnel, which is about 27 kilometers in diameter, that tunnel got contaminated with the helium, and the helium they have to use because the whole accelerator has to be kept at a very, very low temperature, almost near minus 273 degrees, which is a very low temperature. So the whole experiment has been stopped, and now they are checking why the helium leak has happened, and then after the whole thing is set right, it will take almost a year for them. They have to check what are all the points at which this leak could happen, and then start the accelerator again. But many people feel that there is no danger at all, so we should go ahead and test it. Why it is science on the edge? Because the consequence, some people feel, is unpredictable, but many people feel that there is no danger. You know, the same thing happened when genetic engineering was started, and people were worried about man interfering with the genetic process in the earth. So one important lesson we have to learn from all this is that science is always tentative. Science depends very much upon testing what is happening, then getting a certain confidence, and then you go ahead, taking a certain amount of risk whenever you go ahead with your experiments or you go ahead with your... Now, what has happened in the last several centuries is, over the long period, which I'm going to describe very shortly in a brief way, science has developed, but as science developed, there have been radical changes in our fundamental concepts. After all, the objective of science, which you will see, is essentially to understand what is happening around us. We learn quite a lot based upon our common experience and everyday experience, and then we try to understand what is happening around us to the extent that is possible based upon certain concepts. Concepts like space, time, mass, motion, energy, force. These are the very common concepts that we have to use. But as you will see, these concepts had a certain meaning some 200 years ago. But 100 years ago, what happened was there was a radical change in all these concepts of a type that you could never have imagined, that space is such a thing, time is such a thing, and energy is such a thing. There is no distinction between mass and energy, and so on. They were completely total. And this has, as you know, apart from the fact this has led to a lot of technological consequences like development of atomic energy and so on, the equivalence of mass and energy led to the whole field of nuclear development, nuclear energy development. There is also very important implications to the whole philosophy of science, and to know what is real and what is not real. So many aspects which fall in the realm of deep philosophy also have a consequence because of radical changes in our very concepts of everyday thinking. Then we became aware of entirely new universes. You see, we could see before, let us say 300 years ago or 400 years ago, when there were no telescopes, we had some idea of what was surrounding us, the various planets and stars. The stars were twinkling, and we did not know much about what those stars were and how far they extended and so on. What is their connection to us? Why do we have so many stars around us? And what is the relation between the Earth and those? Here, many times I start my talk by asking a question that how many of you are aware about the fact that you have iron in your blood and calcium in your bones? From where did this calcium or iron come? If you think a little about it, and the natural answer will be, look, it comes through the food that I take. It has to come through the food that I take. Then immediately you ask the question, from where did the earth get the iron and the calcium and the various minerals of which we are made of, various substances? Then surprisingly you will find that one atom of iron that is in your body or in my body has come from one star which exploded millions of years ago, and in that explosion of the star was produced the iron atom which has come to your body. And your calcium has come from some other star. And like this, each atom has come probably from different explosions which have taken place at different points of time. This is not fiction. This is a fact, basically, which has been established now. So as a matter of fact, this establishes the connection between us and the rest of the universe beautifully, that both in space and time, each one of us is connected to the rest, is indebted to the rest of the universe, because what we are made of has come from very many different types of objects, which you will see over the last several million years. Then also, you see, this came from the discovery of what we call fundamental particles, new types of particles that are produced, and we got exposed to an entirely new type of universe, which consists of exceedingly small, very, very small, much less than the atoms particles, which many of them are unstable. They don't stay in one fashion. They decay into other particles, but they play a very important role in the whole process of creation and then preservation of energy and so on. Then there also, in the last century, we have discovered in the universe very weird type of objects called black holes and neutron stars, which are very different from what we are accustomed to on the Earth. For example, if a neutron star, 1 cc of neutron star, 1 cubic centimeter of neutron star, weighs more than 1 billion tons. You can't imagine how much. That only shows that what we call matter is 99.999% is all empty space, only a small amount. So you can go on compressing matter to such an extent that 1 centimeter cube of the matter can weigh as much as 100 billion tons, enormous amount of Then I'll tell you about a little bit about this LHC experiment and what was expected and why the experiment is being carried out. And then I'll tell you something about new developments in astronomy. And this is a very surprising development that has taken place just in the last 10 years. We are again on the edge as far as this is concerned, because this has opened up the possibility, which is believed by many today, that our knowledge is only about 2.5% of the total 97.5% of the universe, which is there, which must be there, but we don't know in what form. So whatever science we have developed, whatever technology we have developed, is only a very small fraction of the content of what we call the universe. What the other 97.5% consists of is something that has to be figured out. And now a lot of experiments are being done to see what that is. This is a very, very new development which has taken place in the field of... Now, science has been defined a long time ago as one of the main streams that contribute to the ocean of knowledge, and has been regarded by many as the most systematized knowledge. Dr. Sainis mentioned this, but as you will see in the course of this talk, that this most systematized knowledge may not lead to certain knowledge. In fact, what is happening is we recognize science to be something tentative that is very useful for the moment. We may have to radically change our concepts and our ideas as time goes by, as we gain additional knowledge. Now, of course, there are various definitions of science going back to Plato and Socrates, which essentially focused on the philosophical aspects of science. Then came Archimedes, as you know. He started the first tendency to observe what happens and understand what is observed and derive useful information from it. And then it's only in 1670 that 17th century onwards that science became very systematized, and particularly we give credit to people like Galileo, Newton, and others. Now, Newton said science consists of discovering the frame and operations of nature, reducing them as far as may be to the general rules and laws, establishing these rules by observation and experiments, and then deducing the causes and effects of things. This has become the main objective of science. And this also, as you will see, falls short of what is happening today. And Campbell says in 1921, science is the study of those judgments concerning which universal agreement can be obtained. Because then it came, see, a lot of fights started. Now, there has to be, if a scientific result has to be accepted, there has to be universal agreement on that, not just. Then Feynman, who is an outstanding scientist and a Nobel laureate, he said, nothing is certain or proved beyond doubt. It is not that you are finding out the truth, but you are finding out that this or that is more likely. It is humbled, because we cannot say that science is going to solve all our problems. Scientific knowledge is very important and very useful, but there can be no finality about our assertion about it. Then this is also very true. Neurath says science is like a boat which we rebuild plank by plank while staying afloat in it. Because as we proceed, you see, we find that we are going to sink. Then we put a new plank or something like that and keep floating. Then Charles Townes, who is a Nobel laureate, in fact, he gave lectures a few years ago in this very auditorium. He has defined science in a very beautiful way. This also tells you the limitations of science in a way and why you need religion. Science is the attempt to understand the structure of our universe and how it works, including ourselves. We try to understand what particular objects are, how they work, and so on. Religion is the attempt to understand the purpose and meaning of the universe, including our lives. If there is a purpose and meaning to the universe, then there must be something to do with the structure and behavior. So clearly, there's a relationship between science and religion that can be inferred if we study the matter carefully. An important point that Townes emphasizes is that both science and religion are attempts at understanding, which means that they are tentative and contingent. Now, the universe, if we think a little about it, can be classified into very many different types of universes. You have got the physical universe, that is we are all familiar with, in which we are part of it. Then there is Plato's ideas, and then you have a mathematical universe which is entirely different, because two mathematicians, when they are talking to each other, you won't understand what they are talking about, because they have their own parameters, they have their own equations, they have their own constant and so on, which equations and so on. Then there is the mental universe, which we can sit in a place and think about all kinds of things. And of course, there is the universe of gods, angels, dreams, and so on. Then there's a universe of dreams. But what we are going to talk about today is mostly about the physical universe and its relation to some of the others. Now, science in a way, actually technology preceded science. Many people think that science is first and then technology came later. But if you go through the history, you will find that science, technology in the form of various crafts preceded science by several centuries. And from 3000 BC to 1600 AD, you have all these various developments which are exceedingly important. Then from 1600 AD to 1800 AD was when science began, in a certain sense. Then, of course, this is the period when we started observing with telescopes due to Galileo and others. Then instruments like mercury barometer, pendulum, clock, steam engine, steam-driven car, spinning jenny. As you can see, these are all what really fed the technology and then the various developments as far as the so-called needs of human beings are concerned, because they contributed more towards communication, transportation, living, and then lighting and so on. Then, of course, you have gas lighting, cotton gin, visual telegraph, and so on. Then after 1800, you see, started steam locomotives, steamships, arc lamps, gyroscopes, spectroscope, bicycle, cement, electromagnet, railroad, electric generator, electric telegraph, revolver, safety match, ice-making machines, elevator, kerosene, steel production process, internal combustion engine, typewriter, dynamite, telephone, phonograph, incandescent lamps, transformer, fountain pen, gasoline, powered car, aluminum, pneumatic rubber, electric fan, AC motor, and so on. See, these things, 1800 to 1900, many of us don't realize that what we use today are just 200 to 300 years old. 300 years back, you did not have any of these. There were no electric lights, there were no steam engines, there were no, leave alone aeroplanes and things like that, which came only after 1900. Many of these things which have become our everyday use nowadays were just not there 300 years back. And this brought about revolution in transportation, communication, lighting, entertainment. Then, of course, in 17th and 18th centuries, some important developments took place in the field of science, which many of you who have some background in science will know. The field of Newtonian dynamics, then developments in the field of optics, then electricity and magnetism, heat and thermodynamics. The fundamentals of all these subjects and the various theories were developed about these, the statistical mechanics and so on. Then came kinetic theory of gases, structure of matter. But see, the structure of matter was a very important development by chemists. Then we realized that if you take all the materials that is surrounding us, that can be classified into something like 92 elements from hydrogen to uranium, and everything consists of that. This is a very important development that took place. And it so happened with the help of spectroscopes, when they studied the objects nearby, the stars and the planets, and they found that they are made of the same elements. There was no evidence at that time for anything other than, if you take a sun is mostly hydrogen and helium. And then if you take some other stars, you have the same elements that you have on the Earth. There are no new elements in those, excepting that some elements like, what we call transuranic elements were discovered in special occasions when stars exploded or not. Otherwise, one came to know that the same materials that we have on the Earth, the same elements, constitute the rest of the universe also. This brought in the first idea that there must be some connection between the Earth and the rest of the universe, even in terms of constitution. Then came, certain developments which, as you know, have played an exceedingly important role: theory of evolution and theory of heredity, theory of conditioned reflexes. And then a very important development was, in the 19th century, the electromagnetic wave theory. The Maxwell's theory was responsible for all the advances that we have today. It is Maxwell's electromagnetic theory that first brought out the possibility of producing electromagnetic waves, and these were verified by Hertz. And also, it's interesting that one of our Indian scientists, J.C. Bose, was one of the first to transmit electromagnetic waves from one room to the other. Then, even before Marconi, that is recognized very well now. Though the credit is given to Marconi, the difference is Marconi transmitted the waves across the Atlantic, whereas J.C. Bose did it within the laboratory, actually. But the principle is the same, and then then this brought out a big revolution, a whole revolution in communications. And then what we are able to do today is all because of electromagnetic waves. And then came three important discoveries came towards the end of the 19th century, that is discovery of the electron, discovery of X-rays, and discovery of radioactivity. In 3 consecutive years, 3 major discoveries were made. And these again, as you're all familiar with, revolutionized many things in science and technology. As a matter of fact, it's the discovery of the electron that led to the whole field of electronics. Then you have radio, television, computers, radar, X-ray machines, refrigeration, vacuum, superconducting magnets, lasers, particle accelerators, detectors, and then came the atom, hydrogen, neutron bombs, radio telescopes, space telescopes, tomography, nanotechnology, IT, internet, email. All this is 20th century revolutions. Then, of course, on the theoretical side, this is where the tentative nature of science becomes more apparent. See, it turned out that some of these discoveries, like discovery of the electron, discovery of radioactivity, and the properties of light as they were examined from any body that is heated, told us that we cannot understand these in terms of whatever ideas are there. Then came another very important discovery that if you measure the velocity of light, whether you are moving towards the object sitting on some source, some object, and then moving towards if 2 objects are moving towards each other, then their velocities must add up. That's common sense, and that is what we assume in normal classical dynamics, and it's called addition of velocities. But it turned out that surprisingly in the case of light, the velocity did not add up at all. If you try to approach the light, then instead of velocity changing, the color of the light changed. And similarly, if you receded from the light, instead of, again, velocity becoming minus, it became the color of the light turned to blue. So these things could not be explained. And it is in this connection that Einstein came with his special theory of relativity. And the special theory of relativity, I don't have time to explain it, but what it essentially means is to be able to understand making the constancy of light as universal. That means it doesn't depend upon with what velocity you are moving towards it or away from it. Can be explained only if you fuse time and space. The 3-dimensional space concept and the 1-dimensional time concept have to be fused into one. As a consequence of that, very strange things happen, and it has been verified. That is, if I am moving in a very fast train, that not at the normal velocities of trains, but at a very, very fast train, then the rate of flow of time in my train will be different from the rate of flow of time elsewhere. So we thought till then, according to Newton also, that the rate of flow of time is the same everywhere in the universe. It cannot be one rate of flow of time in my laboratory and another rate of flow of time in a distant star. It had to be the same according to old ideas. But now it changed completely, and not only time, but space. If you had a meter stick, and then if it is 1 meter in the system in which I am moving, the other system with which I am moving, it will measure a contraction. There will be a contraction of the length. So space and time became relative concepts. They were no longer universal. You had to think of a system in which space and time change their very nature, basically, because they are no longer the same all over, the same all the time. We thought that space and time will never change, that they will remain the same. In fact, that's the basis on which this whole standards were made. But that had to be given up. Then also, following this, a lot of new discoveries were made. The atomic structure was found. And then, in the atomic structure, they found, with the help of radioactivity at that time, that the atom is not a solid material. There is a central nucleus which contains all the material, and around it are the electrons which go around. And there's a lot of empty space in between, in the atom as a whole. Atom itself is quite empty. Though the center is a very, so when you have material consisting of atoms of any elements, it turns out that 99.999% of it is all just empty space. See, right from the time of Newton, there was a problem. Newton said that, look, there is a force called the gravitational force, which is responsible for the planets to go around the sun, various. But he did not tell us what is the force and how is the force produced. He said, look, this force goes on decreasing as 1 over r squared, the inverse square law. But he did not give us a mechanism by which the force operates. But still, it was operating. So this action at a distance was a big problem right from Newton's time. And when somebody asked Newton, what is it? He says, God alone knows. I don't know how this gravitational force is produced, and I don't know what happens in between. All that I know is you have something happening which is, so the whole, in this connection, the idea of fields was introduced. Because one, again, brought in, for example, even in the case of electrical charges and an electron going around a proton in a hydrogen nucleus, the same situation arose. The nucleus is very small, the electron is quite a far off distance. How is the force transmitted? So they started giving importance to something in between, which we all thought till that time was empty space and nothing else. This brought in the idea of various types of fields, electrical fields, magnetic fields, electromagnetic fields, etc. So slowly the idea of vacuum being just empty also had to be given up. Then came a series of new discoveries. That is, when a high energy particle comes and interacts with the atmosphere, then in that, I'll just show you a picture of that, new types of particles are produced. First act of creation was seen in cosmic rays. That is, these particles come and collide, and then new particles are created. The question naturally comes, where were these new particles? Are they in the particle that comes in some form and then it breaks up? Are they in the something that happens at the point where the collision takes place, etc.? The creation of particles became a big question. So a lot of investigations had to be done, and that is why they started building up larger and larger accelerators, because for this to happen, the particles had to collide with high energy. So they went on, a large number of accelerators were built in different parts of the world. We don't have any very high energy accelerator in India, but there are accelerators at Geneva, accelerators in Fermilab in Chicago, and so on. Very high energy accelerators started. And then they also found some of these particles that are created, you see, they decay into other particles. So new other particles also were discovered. So we discovered an entirely new universe of fundamental particles. Here, for example, a particle comes and suddenly it changes its character and becomes something else, and a little later it becomes something else. And so the chain of events taking place in the whole micro universe. We had to understand that. Now here, for example, is a beautiful example when a high energy gamma ray comes in and then it scatters off an electron, and two new particles are created. At the bottom, you can see here a pair of particles. And these pairs of particles turns out to be the first evidence for the creation of what we call antiparticles. Till then, we did not have the idea that in as much as we have a proton and an electron, we always wondered why it should be positively charged proton and negatively charged electron. Why not the other way? Negatively charged proton and then positively charged electron. There it is. Then later on, they discovered there are antiparticles. And it turned out that these have to be produced in pairs. Whenever production takes place, you have to produce particles and antiparticles. And then unless they decay into something else, antimatter and matter, if they came together, they would just explode into something like a huge ball of radiation, basically. And that is the reason why, as you will see, people got worried about this whole question of black hole creation. Now here you see one particle comes from the top and then collides with a nucleus, bromine nucleus in a photographic emulsion, and then you see a large number of secondary particles. All these are called mesons. And then there are various other types of particles. The same thing, you can have a heavy nucleus coming in and you can produce large number of. These actually are the first acts of creation in the universe that we have evidence for. A large number of properties of these I not go into. And one other very surprising thing that came out of all these developments was, if I have a proton, I think the proton, if it goes from here to there, it will remain a proton. But if you examine it in terms of shorter and shorter and shorter time intervals, then you will find that proton no longer remains a proton, but it becomes in between a proton and a pi zero, then that pi zero becomes something else, that something else becomes something else like that. And again it becomes a proton. So in the universe, what we think, the important point to notice here is that nothing remains as what it is. It is continuously changing. It's your capability for examining that in sufficiently short times with the proper apparatus that will reveal the truth. So what you think as something stable that is sitting in this table or in this as a proton, because after all, the proton sits in everywhere, in all of us, etc. But its nature is chanchala. That means it's continuously changing and again coming back. This is one property which our ancients have talked about in a different way. But this is a fact that has been recognized now with the discovery of particles. Now let me come to this collider, which is a very large machine. 27 kilometers is the diameter of the tunnel in which these 4 accelerators being built. And this produces very high energy particles, and then you see particles go in one direction and then antiparticles in another direction. What they try to do is to make them meet each other. Then they get a very high energy, and in such high energy collisions they look for something called a Higgs particle. Why Higgs particle? The Higgs particle, we have all these various types of particles which I have described, electron, positron, then proton, neutron, everything. We did not know how they got mass. Why? What is the difference between one particle and the other particle? The difference is mostly in masses. Then why is it that the electron has a very small mass? Why is it that the proton has a larger mass? What is this proton mass content? So for this, there is a theory that there must exist some particle called Higgs particle, which is a very, very massive particle, and that has a field of its own. And if these particles just pass through that Higgs field, they will start catching some mass kind of thing. Now, the discovery of that particle is very important for the present understanding of the fundamental particles and the entire theory of physics. This is a very important discovery that has to be made, and that is the reason why they built this accelerator. So far, all kinds of predictions have been verified, but this one prediction that there must be a very massive particles produced in high energy collisions has not been verified yet. And the question came whether in such a collision you can produce what is called a mini black hole. Some theorists said yes, it must be produced. And mini black hole is, I'll come to it, and it came in the connection with astrophysical concepts. But main idea is it's a very small entity, but in which enormous amount of matter is concentrated. So much so the gravitational field around it, because the mass is so high, is very strong. And it is so strong that even light cannot come out of it. Even light bends around it and gets remain. That is why it is called a black hole. Mini because it's a very small one. And such particles, if they are produced, one of the properties, the black hole, any matter that is around it goes on accreting the matter, becomes a bigger black hole, bigger black hole, bigger black hole, and the end is disastrous. So they wanted to know, firstly, whether, but Professor Hawking, about whom we must have read in the newspapers, said even if a mini black hole is produced, it will just immediately, explode into gamma rays. If it does that, there is no worry. But if, on the other hand, it stays there and starts accreting matter, then it becomes a big, dangerous thing to happen. Now, that is what they are looking for at the CERN accelerator. Now, this is the kind of scenario in which they are expecting the Higgs particle to come out. Now, I must also tell you a little bit. I don't have too much time, but I will try to do it in 10 minutes. Sangeeta? Huh? 10 minutes? Okay. You see, in as much as in the field of physics, so much development took place, physics and chemistry, similarly, a lot of development took place in astronomies. First, we had optical astronomy. That means with the larger and larger telescopes, we discovered what is there beyond, what's the constitution of stars. And when we saw big disks of radiation, we found that each one of those disks is a galaxy by itself, something like 1 billion stars in it. The distances are enormous, etc. The true shape and size of the universe, we became aware through optical astronomy. Then in 1930s, one started discovering that these objects are also sending us information in the form of radio waves. That became radio astronomy. In optical astronomy, one very interesting thing was observed early in last century. That is, these galaxies, which are a huge collection of stars, were not stationary. They are moving away from each other. And then they discovered a regular pattern in the movement. The larger the distance between two galaxies, the greater with which they were receding. That means there was a pattern in which of universal expansion, in which the larger galaxies moved faster and faster away from each other. And it so happened that if you put them all together, they could all be at one place together. That is what people wanted. And this is what led to what is called the Big Bang theory of creation of the universe. The universe, we think, all these have been there forever. It's not so. According to the Big Bang theory, there was I'll come back to, there was a moment of creation of the universe. The explosion took place, and immediately after the explosion, a very hot plasma was created. And in the plasma, the fundamental particles were created. And the fundamental particles joined together to make matter. And these material particles like protons, electrons, etc., gradually accreted and formed what we call the stars. From the stars came the galaxies. And when the stars exploded, you see, then they became, you could have at the as remnants of the star, objects like what we have now. And for example, the sun is one of the smaller mass stars, and then which is just hydrogen, plasma of helium and hydrogen, whereas some of the other stars have other materials also. And in the explosion, new matter is created. This gets dispersed because of explosion, huge velocities, etc. So an entire theory was created as to how the universe could have started. And now they have been, with the various velocity measurements, etc., they have been able to say that this happened at an exact time, 13.6 billion years. A billion is 1,000 million. Billion years ago, all the entire universe was together, and there was a point which exploded, and all these various things took place. Now, this has happened. Now, you see here, if you look at it, there's a man sitting there looking at this whole thing, pondering as to, that is how, in fact, as Einstein said, one mysterious thing is that we can understand how the universe is mysterious, but the point is man is equipped with a brain to be able to understand how all this whole creation is made. So in fact, it is in this connection when they started looking at the various types of objects, then as the new astronomies came into the picture, X-ray astronomy, gamma ray astronomy, high energy astronomies, neutrino astronomy, each radiation has its own astronomy. We got more and more information about the universe, and we have been able to now construct a beautiful picture of the whole thing. But, sometimes one drop of acid, you put it on milk, the whole thing goes bad. So something like that has happened. We built a beautiful theory of space, time, laws of nature, and all that to understand everything that is happening. But about 10 years ago, some strange discovery was made. And that is that the universe is not only expanding, but is accelerating much too fast according to this theory. And that was again experimentally verified with, because of the advances in space technology and telescope technology, communications, etc., they have been able to put an optical telescope in a satellite called the Hubble telescope. That has been responsible for a lot of information. And combining together various observations, they find this evidence for a universe that is expanding faster than what they had thought. This faster expansion meant that there must be a force. That is, the first initial explosion gave the necessary force for it to expand. But then, because of gravity, after some time, it had to contract. They were not sure whether it is going to contract or not, but they never expected that it will expand further. So now the new idea is that there is what is called dark energy, nature of which we don't know, but it has a very different property. Instead of having the attractive nature of gravitational force, it has the opposite. It has a repulsive force, gravitationally repulsive. So these two, at large distances, the other one takes over, the repulsive force takes over, and that is responsible for the acceleration of the universe. And it turns out, when you make the calculations, that what you need by way of this dark energy is much more, compared to the energy that we have in the form of normal matter. So there's a big discrepancy between the two. And also, these galaxies, if they had to be bound by the usual gravitational force, they found the matter that is there in the galaxies is not enough. There has to be some other matter. So they have now come up in the last 20 years, the idea that there is something called dark matter, the nature of which we don't know. And more recently, there is the concept of dark energy, which is still more puzzling, which has the gravitational repulsive force, and which fills up the universe much more. And that is, as I said, we know only about 4%. See, these figures slightly go on changing, but the current idea is that known matter is only 4% of the total energy of the universe. The remaining 96% is unknown. So what is it that we learn from all this? See, this is the how the energy is distributed. Dark energy predominates, then the ordinary matter is a very small fraction, 3.5%, and then the dark matter about 26%, and so on. So the other thing that has been found is that there's a connection between all this. They have built up what is called a grand unification theory, and this is what this particular picture depicts, that there is a connection between what is happening through all these various theories, what is happening in the micro universe and what is happening in the macro universe, because according to the current ideas, which I don't have time to describe, everything ultimately is a property of space, filled with everything that is going to be discovered, even in the future. So there is a lot to be done in terms of discerning the total characteristics of the so-called quantum mechanical vacuum. So at this point, I will leave you, and you can ask me any questions.
Professor Sreekantan, welcome questions. I request you to please raise those nameplates, so that I can have an order, and in that order we can go ahead with the analysis. First presentation. Can I ask? Yes. Thank you very much for giving the lecture. I just want to know a few things. As I can see, the Big Bang theory for creation of the universe is well established. So there is no reason to believe why it should not happen. As I have understood, that physical laws as we understand today by the humankind will definitely not be valid in all frame of references. When you go back in time, let's say at the time of creation of the universe, the sudden state is defined up to the time of 10 raised to the power minus 42 seconds. So question is first, what was the state of affairs at the time of creation of the universe before 10 raised to the power minus 42 seconds? One. Number two, what is the concept of quantum consciousness?
No, as far as your first question is concerned, we don't know. The point is, there are four forces in nature: the electromagnetic, the gravitational force, the electromagnetic force, the nuclear force, and the big force, that is the one that is responsible for decay of fundamental particles. There's some evidence that all these forces could be one and the same, provided you do them at the proper distance. You measure them at their properties at the proper distance. And the longer the distance, then they show their peculiar characteristics. But as far as so far, one has been able to formulate theories according to which the gravitational force cannot be included, but the other three can be included in what is called the grand unified scheme. But gravitation, it has not been possible to understand. A lot of experiments are being done whether particles which are called gravitons are emitted by some objects when they explode or when the neutron stars are spinning and so on. But this 10 to the power minus 43 seconds essentially comes from the quantum mechanical considerations. You have what is called a Planck mass, Planck time, and so on, which are all related to each other in terms of we have a certain uncertainty associated. In quantum mechanics, what an important thing is that the certain parameters cannot be both determined, cannot have the same value, precise values at any one point or one velocity and one position and so on. You can either know the position of the particle and not its velocity, or very accurately, or you can know the velocity and not know the position and so on. So there are a lot of uncertainties involved. So we don't know really, when you go to 10 to the power minus 43 seconds, first of all, whether the same laws that we have formulated in ordinary space and in large distances, large time intervals, etc., is valid at all. This is a very important question. That is why we don't know whether there is a barrier there about even the loss of, because according to Big Bang theory, interestingly, is this what I call as vacuum had to be created first. It is vacuum that expanded. It is vacuum that got the high temperature in the form of plasma, in the form of particles which are known as XY particles and later quarks and so on. The plasma consisted of these, and out of these the protons, electrons, etc. were formulated. So we really don't know. As a matter of fact, some people just describe the Big Bang as once upon a time there was a point which had infinite amount of energy. It looks like fiction, you see, and that exploded and provided that created the not only created vacuum, but it also had to create the laws of physics. It had to create the constants of nature. Because you see, there is no theory which can tell you why the electron should have this particular mass accurate to 8 decimal places or 10 decimal places, which you have determined. But it is so. Wherever you go in the universe and try to measure the mass of the electron, whatever material you bring and then measure the mass, it's the same. So there is this anomaly about constancy on the one hand. So at the moment, we have to be humble and say we don't know what really happened immediately after the Big Bang. But the beauty is after that initial uncertain period, we can construct a reasonably accurate theory. The other question is about quantum hypothesis. That's a little,
Quantum consciousness.
quantum concept. You see, quantum concept means
Quantum consciousness.
quantum consciousness. Well, people have started talking about it, but I don't think I can do justice. We have to go into a little more details about, the structure of neurons and neuronal transmissions and neural. I can explain to you separately. I'll do it.
Next, Mr. Tansal. Shashigiri.
Good morning, sir. My question is.
No, we'll come back to you.
My question is related to the universe. Actually, there's lots of research on the shape of the universe and the edge of the universe. Do we have an answer to the shape as well as how many millions of light years the edge of the universe? And then the second is the unified field theory. Actually, the unified field theory, a few years back, it was in the forefront of the research, and one of the Asian also got the Nobel Prize. And still, the current research is active on the unified field theory.
So, what's your question?
My question is on the universe. Two questions. One is related to the universe, the shape and the edge of the universe, whether approximately is known, and the current research on the unified field theory, what is the status?
Yeah. See, as far as the universe is concerned, we essentially depend upon what is called the Doppler effect. That is the relation between the shift in the frequency of light and the velocity. Simple Doppler effect actually. And that has been measured. And with that we are able to say that there are objects at various z values, that means the redshift values. And on the basis of that, we can calculate. And that is something like I wrote in 10⁻30 centimeters or so is the present idea of what the universe is. The interesting thing is that in the Big Bang theory, when it created the vacuum, the space, so the question came into what this vacuum expanded. Was there space before? That question has no meaning according to the present ideas, that what you are creating is space itself. Before that there was nothing there. There was really absolutely nothing. So the idea of the universe, when you say, is now from the accelerating universe, it is continuously increasing.
So the side.
Listening to you, start thinking about what you said. You made a comment that the technology preceded science before 17th century. I'd like you to substantiate and give more give us information. What led you to think this? What led you to think that the technology preceded science? And maybe I have the other question also is that you also mentioned that every element on this earth has got origin of a star explosion. And obviously the universe has not become static. The explosions are happening. Does that mean that the more and more new elements come to the earth? This is one curiosity which comes to it. And the way you explain the science, how it has grown and what is there today. Other than this linear, the third experiment which is going on about the black hole, what are the major breakthroughs or major events that are foreseen in the near future, which gives us to explain about the science on the edge.
You see, as far as the first question is concerned, let me come to the last question first. You see, what new discoveries are expected is difficult to predict, but we know what need to be explained. We have to understand on the basis of physics. See, the whole of chemistry is explained in terms of physics, and the whole of biology is explained in terms of chemistry, mostly. See, a cell is supposed to be just a very complicated chemical factory. Now, we have to understand what are the processes that are taking place inside the cell, what is responsible for the building, how the DNA came into existence. Many of these problems they are not understood. The first, if you want to talk purely in terms of its constituents, and understand how the information is coded to DNA, etc., we have got to have an explanation for how these things happen. Okay, this will keep us busy for a very long time to come, because only now we have been able to discover some order, how the various elements are constituted, and how the various properties of the elements come about, and so on. And one interesting fact is that if you see carbon, hydrogen, and oxygen can form sugar, can form fatty acids, can form also hormones. Basic constituents are the same, but the properties are so different. Why do you think the properties are different? The constituents being just the same elements, but the properties are so different. The understanding now is that they have different structures. Somehow, structure and property is related. In fact, interestingly, this is the same old idea of Plato. See, Plato said ultimately it is forms and structures that are responsible for all the thing that you see. So that is one direction in which a lot of work has to be done. We have to understand the universe, and even leave alone the universe, the human beings, the animals, the life in terms of physical chemical processes. If you believe that there is no life that is put into it by some miraculous process or by some other divine enthusiasm, if you want to explain life in terms of the physical chemical processes, a lot more work has to be done. That is one area in which people. Secondly, the area of consciousness studies, we don't have an understanding how the neurotransmitter chemicals and the just electrical signals that are produced by the various sensors and the neurotransmitter chemicals that are released in various places ultimately give you all the thinking processes, all the sensations, all the thoughts and the various things. How do they arise? They belong to an entirely different realm. But if you strictly want to understand it in terms of only the physical constituents, then a lot more has to be done. That is why one of the important areas to talk in a very general way is the whole area of emergence. See, there are very many special properties that are emerging as a result of circumstances. For example, you take this entire area of nanotechnology, which is now making so much of headway. What is the difference between the nanotechnology and other particles? These are the same particles. In fact, Professor Henry always says, if you take hydrogen, and if you put more than 100 atoms of hydrogen, then it becomes a conductor. Before 100 atoms, it behaves like 100 molecules, it behaves more like an insulator. Now, why this sudden transition takes place? These are all to be investigated. I'm only giving you some examples how there is plenty of scope for new directions to emerge. leaving alone the very sophisticated areas I talked about discovering the new types of particles that are there, and then according to present theories, corresponding to each fundamental particle that we have seen, there must be another series of fundamental particles which have different properties. We have what are called, supersymmetry and so on, in which corresponding to an electron, you must have a electron, corresponding to a muon, you must have a spion. Like this, there are so many predictions like that. That will all come gradually when we have more and more accelerators and higher and higher. But it's also possible that we have reached the limits to which we can go, because even this present experiment, costs about $10 billion for them. The accelerator costed them $10 billion. Initially, the Americans were building one. They spent $2 billion in the US, in Texas, made a tunnel, but then they found it's too expensive and gave it up. Now the CERN collaboration has been able to get money from various countries and been able to bring that almost into an operational situation. In astronomy also, there is so much new being done now. There's a whole field of very high energy astronomy where we are trying to look for particles of super high energy, 10 to the power 22, 10 to the power 24, and so on. Because the question comes, up to what energy can you accelerate particles? What are the mechanisms by which you can accelerate particles, and so on. So there is an enormous amount of new fields to be investigated.
What is the other question? What is the basis to say that technology precedes science?
You see, technology, for example, that is, the potter's wheel. There was no technology. This was only by experience and by handicraft. Potter's wheel is not one, or even the old type of cartwheel. All these things were all done by just crafts. Craftsmen did that. Even the pulley, lever and all. There were no scientific principles involved in that. The scientific principles started coming only after the time of Bacon. And they started putting, these probably they were there, but they systematized knowledge. And then they put them into laws, they put them into some kind of a systematized knowledge.
Next is Sreekantan.
Yeah, I have two questions. One is on black holes. Are the black holes exist in the universe? What are the evidences? How do you find black holes? Other question is
Maybe
antimatter.
can we limit it to one question?
Yeah.
There's still more people to ask.
That's a very interesting and important question. When a star explodes, depending upon the mass of the star, a certain remnant is left in the center. The rest of it all escapes. Star explodes because, as the star is made of various types of material, and when the temperature is very high, you start burning away one after the other. First hydrogen goes, then helium goes, then carbon, etc. Finally, you are left with a situation where there is a narrow core, and that either can explode, and at that stage, what can happen is that still a remnant can remain. It does remain. Now, if that remnant mass is more than a certain value, then it forms what is called a neutron star. See, what a neutron star is, the central portion, when all the outer forces are gone. See, the star is being maintained in its condition by two things. One is the radiation pressure, which is pulling it out, that is going out. Then there is the gravitational pressure, which is collapsing it. So, when all the outer material is gone, the gravitational force alone operates, and it becomes smaller and smaller and smaller. And if the mass is not too large, then you see it becomes a neutron star. What is remnant? But if the mass is too high, supposedly there are lots of 3 or 4 solar masses, then what happens is, you see, even in the case of condensed collapsed objects, you have got protons and neutrons and some electrons. and there is some pressure for them to lose their identity. But in the case of black hole, what can happen in mass is too large, all the identity is lost, and what's called the de-inercy pressure also is overcome, and then it collapses further and further, and then it becomes a black hole. Why it is called a black hole is in its neighborhood. You see, light also, surprisingly, is not a particle without mass. See, light, the photon, has a mass, and the mass depends upon its energy. The famous equation of Einstein equals mc squared. If you know the energy of the photon, then you can find out its mass. So that mass is such, the gravitational force between that mass, photon mass, and the central object black hole is such that light cannot escape it. It will just remain within the, so you can't normally see it. But the way it has been identified is, you know, if there is another star which is going around this star which has collapsed, which is a black hole, and if there is another star which goes around it, these are called binaries. Then mass from this will be attracted by the black hole. And when that happens, as the mass dust goes closer and closer to the central object, it starts rubbing, they start rubbing against each other, and very high temperature is created before it goes to a region where it cannot come out. And light that is emitted in that region has been detected. So this is a property that has been detected by identifying, but there are other characteristics to find out what should be the mass by the binary characteristics and so on. But to call it a black hole is essentially the detection of very short pulses of radiation that come out when infrared X-rays, gamma rays and so on, when matter is accreted.
Next is Rajasthan.
So this has been very interesting, also interesting,
Little louder.
this has been a very interesting exposure to the field of science. And personally, like, thank you very much for this. I have a special interest in this subject, that's why I will go straight away to the point. First one is Professor Susskind, while being very critical of Stephen Hawking, especially in the explanation of singularity, did mention, and it was brought out very well in Brian Green's book on Arabian universe, that that the only explanation which Stephen Hawking could give is the existence of parallel explanation could only come to if there is an existence of parallel universe and also multiverse, which of course Professor Susskind rubbished it. But what is your thought about it? Is there a possibility? And second is the Higgs boson particle which the Large Hadron Collider is trying to get in CERN. Would it be helpful in getting the string theorists and the gravitational people together on the 11th dimension? Will it bring about the unified field theory?
First thing about Susskind. Second question is the reality.
Probably you can discuss this separately because the idea of parallel universes is there. Essentially, it's part of some problems in quantum mechanics. You will talk about it separately. Yeah.
We can take more questions. Please keep the questions short so that because we still have 4 or 5 people on this. Mr. Samanand.
Sir, I thank you for the information you shared. Sir, I am a little bit disturbed. You see the way we are advancing in science and technology. You know, the title itself said the science at the edge and on the edge. You know, it has given us more questions, you know, as we advance than the solutions. Where will it lead at last the humanity? We are all looking for peace of mind, peace of life, and so on and so forth. our forefathers had a better finale, you know, what we are having today. We have 100 channels in the TV, but we have 24 hours a day. That has not changed. You know, finally, where this science is going to lead the humanities?
Well, the other way it is said that science gives you a lot of knowledge, but not wisdom. So as far as, not necessarily wisdom. See, as far as your first, that is why you remember Professor Charles Towns, he said that science alone will not be able to give answers to all questions. You need religion. Religion means some kind of faith is necessary and some other avenue of exploration of knowledge. That is absolutely clear. But science can only give us more and more power. And how it is used depends essentially on, you know, why are we worried so much about bombs today? Yeah, the atomic bombs. Because if it goes into the hands of, you know, wrong people, then it can be totally misused, and there is every danger of that. But the question that comes up is, does that mean we should give up developing some of these things? Same thing came about genetic engineering also. You see, with genetic engineering and cloning and things like that, disaster can ultimately result. But people have not given up. They have still continued, thinking that wisdom will come from somewhere. That is the only answer I can give you as far as that is concerned.
Mr. Suresh.
You have given a very good account of the progress of science over the centuries. And for a person like me who understands very little of science right now, there are more knowledgeable people in the gathering. What I understand is that whereas whatever was done, let's say 200 years ago, was simpler and more down to earth, which the common man can understand today, what is happening today is much more complex and very costly. So I was just wondering, and you partly answered that what is the future of all this, ultimately? We are spending so much of money and energy on the scientific inventions. And then I connect it to the last question that was asked, but how does it really help the common, human being? And I also wanted to ask you that the Indian philosophy, if you, look at that part of it, which has to do with more with peace to the common masses, has that any connection to these developments which are taking place in science? Is the answer like there, or how do you look at this?
See, as far as the first question is concerned, where it will lead us to, it's difficult to say. But, point is, you take, for example, nanotechnology, which is one of the things in the forefront of scientific investigations. What people are hoping is a lot of new products will come. You'll be able to harness solar energy at a much cheaper. In fact, there are already people who are advertising that you can just spray some nanomaterials on a long roll of paper and spread it, and then you can catch solar energy. Such dreams are there, and some of these things will probably also materialize. So there is no question that as far as the material improvement of humanity is concerned, science is required and science will advance and will provide. The second question is about medical advances, the types of things that are being done by way of surgery and by way of medicines today. In fact, again, nanotechnology is being quoted for making materials in such a way that they can go through the stream of blood and then go to a particular point and deliver the medicine there. You see, that kind of things are required because, in the case of cancer and in the case of things, the side effects are so large with the present doses and all that. If you can develop a system which puts the whole thing in a proper place, The second question is, in fact, I sometimes give a lecture on the parallelism of insights between modern science and ancient philosophies. In fact, you are very right that some of these insights which you are having about particularly the idea of quantum vacuum being the ultimate, ultimate reality as a matter of fact, from which everything emerges, beautifully fits in with the concept of Advaita philosophy. Ultimately, there is only one entity, transformation of which is responsible. You don't need God, you don't need, it's only ultimately one entity which is responsible for everything else. Sarvam khalo idam Brahma, or something like that. You see, that idea has been there. But there is a big difference between, that approach that can only appeal to the intellectuals who really go into that. And finally, Shankaracharya, everybody will tell you, if you really want to know the truth, you must yourself realize it. There is no way in which you can know about it through any experiment or something. You must yourself realize it. But that's a different thing compared to the totally objective way of doing things in science.
Dr. Amarjit.
Sir, your lecture was very interesting, and you have given a very, very good lecture regarding the origin of universe and the development of science in the course of time. In this connection, I want to ask a question which all of us are asking, that that there's a talk of so many UFOs, unidentified foreign objects, and is it that any intelligent beings they exist in this universe? And then what is the question of God? The normal thing is the God is there somewhere. And what do you have to say as a scientist regarding these two things?
Well, about question of, there is a lot of effort being spent on trying to see whether there is evidence for, of course, they are trying to see whether life is there in some form or the other elsewhere in the universe by, some of the satellite experiments, some of the landing probes and things like that. Even on Mars, there is life also. But as far as advanced civilizations is concerned, the question is, there's no question of anybody being sent there and coming back, or anybody coming from there here, because even the nearest star, it takes, nearest star is at a distance of 4.3 light years. A light year, the distance, one light year means that velocity of light, which is something like 3 to 10 to the power of 10 kilometers, centimeters per second, has to travel 1 year to reach the nearest star. So the distance is enormous, so it's just not possible for only communication is possible. So people are trying to see whether some communication is coming to us, some information is coming to us from another civilization. In fact, a lot of experiments are being done there. When some objects called pulsars were discovered about 30 years ago, their results were not published, essentially because the pulses were so regular that at that time people thought this must be some signal being sent from some other civilization. But later on they found not one, but 2, 3, 4, and they found out the reasons why this neutron star hypothesis came and so on. So that is gone. I mean, there is no idea now that this is signals coming from, but still people are looking for it. Not only that, in some of the American space probes, they have sent kind of, they have etched on a metal plate, you see, various positions of these pulsars and the solar system with respect to that. And then man. So if somebody by chance catches one of those things, he will know that there is a civilization at some such a place. So that kind of attempts are being made. But so far, there is no evidence for anything extraterrestrial civilization.
I think as far as the question of God is concerned,
as far as the question of God is concerned, I'll tell you, my own feeling is the following. God is more a personal, faith, should be, rather than you cannot prove by any, even our own religions will tell you that you cannot prove God except by personal conviction.
Next, Mr. Dharmadikari.
My question may sound a little absurd. Over 100 or thousands of years ago, there was a monkey, and the monkey has become man today. as you said, we have in us the iron and the calcium, which has come from the broken stars. During next few years, 100 years, or how many years, more stars would break. We'll get more iron or calcium. So will man become a Superman? And we can handle his day-to-day work and as well watch 100 channels in 24 hours.
Well, that again is a question of time. You see, if you go according to the evolution that is taking place, natural evolution, we don't know what's going to happen when we start interfering with evolution by all these new genetic engineering and so on. But if you leave it to nature, it will happen. Because that is how all the, as just now said, man has come from monkey. But how long it will take, million years, 10 million years, for a superhuman being to evolve is not that clear. Because again, it's a question of many, people must die, and then somehow there has to be need for a better improvement, and then in our design and things like that. It should all happen naturally by natural selection and so on. If you go according to theory of evolution, there is no reason why man should not evolve further. On the time scale, we don't know, we cannot say in what time scale he will. As a matter of fact, there was a scientist by name Delbruck. You see, the present man can only think in terms of 3 dimensions of space and 1 dimension of time moving forward. But according to science, you see, space is not just 3 dimensions, and time and space are not tied together. So you need a different, and this we cannot even envisage. We cannot envisage a 4-dimensional space and time. And we can, and according to some theories now, you need a 10-dimensional space to really understand everything. So this is all limitation of the human mind. So what Delbruck says is, it's quite possible that a man who evolves after 1 billion years may be able to think differently. In as much as today, as a human being, I can write a computer program. A monkey cannot. That's a result of evolution. So we may be able to think very differently much later.
Last question, Mr. Vinod Shah.
Yeah, my question is, it's very difficult for me to believe that nothing existed before 13.6 billion years. So that leads me to a thought that probably the universe alternates between creation and destruction, expansion and contraction, and this gives rise to some more thoughts that there may be some universes which are currently in contraction mode and currently in expansion mode, and probably there is some phenomenon happening which science can explain if 2 universes interact. So I just want to know your reaction to these thoughts.
Yeah, you are very right. As a matter of fact, this Big Bang theory is one of the theories which is finding the greatest favor today because of certain observational evidences. At the same time, there are people who believe in what is called the oscillatory universe, in which this expansion takes place, then it contracts, and again you start another cycle like that. And there are also universes, not only one. See, Big Bang creation, why should it result only once? It should happen. Why not many times it should? So there may be many, many parallel universes which we can think of, in which Big Bang creation could have, similar Big Bang creation could have taken place. It could have evolved differently. The constants of nature could have been different. And there could be other types of human beings. But there will not be interaction between the two at all, because for interaction to take place, certain types of forces are required and all that. I entirely agree that this is one of the theories at the moment which is most popular among the scientists. This recent development of accelerating universe has again made us think about the Big Bang more seriously.
Any more questions can of course be taken up during, if you don't mind, we are 10 minutes behind schedule. Finally take it up.
Thank you for your valuable lecture. Apart from emergence of life, is there any other possible processes possible? Apart from emergence of life in the universe, is there any other possible processes? Number 2, all have any estimation or scientific prediction on the life period of this universe?
Or we can discuss it over here.
Thank you.
I request Dr. Sainis to make his closing comments and a formal vote of thanks for P.V. Sreekantan.
Friends, you will all agree with me that we all heard a very erudite exposition of fundamental science and an entire spectrum of discoveries over the last 4 centuries, and that has brought our human life to what it is now. And then there was also a peep into the future, saw it. Then he took us to the 18th, 19th, and 20th century discoveries in science, finally concentrated his effort on high energy particles, different fundamental particles, the expected outcome of the LHC experiment, and convinced us that matter actually is a chanchala, is ever changing. He expounded the concept of black holes, the new universal concept or unifying theory, both micro and macro grand unification theory of those. And finally, he told us about the dark matter and dark energy, the ever expanding universe, and how these concepts would explain that universe and contain it. Finally, I think, in my opinion, the take-home message was as follows. Science gives us a lot of knowledge and not wisdom. The applications of science, as Nobel laureate Yerne once put it, precede the development of science itself. Science gives us more power. How to use it is left to us, and that alone will guide the destiny of our human race. Ultimately, philosophically, we finally gravitate to the concept of Sarvam Khalvidam Brahma. Finally, everything is unifying into one. I think that was an excellent exposition from Professor Sreekantan. Thank you very much, sir, for this wonderful presentation. Yeah, and now on behalf of all of you, I would like to present this memento to Professor Sreekantan.